the WKB approximation for black holes perturbation theory. So if you read it, the floor is yours.
Hello. Okay, so use this. Firstly, I'm not sure how many of you work in black hole perturbation or work in maybe had read this kind of WKB approximation before. But basically, this talk is the reviewing presentation. It's not my new work or anything, but it's reviewing some reference. Okay. Okay. Oh, basically, if you have question, you can stop me anytime and ask. Okay. And okay, starting with the introduction. So, WKB. Eh, no, like. Oh, okay. Okay. Okay, okay. So the WKB, or sometimes we call JWKB, is because around 100 years ago, exactly 100 years ago, and 102 years ago, these people and doing some, starting to doing something called some serious solution. Now we call it WKB, but previously we still not use their name to name it, right? So we call it. They start to doing some serious solution for the linear ODE, and we usually physics is called WKB. But actually, earlier, maybe 2 years earlier, Jeffrey also worked in this and gave some fundamental thing. So if you see some reference, and they will say JWKB or WKB, but it's the same thing. And it's this method can obtain in a global approximation to the solution that of a linear differential equation. And the key idea is they expand the solution as the exponential series. Okay. So basically, not only in black hole perturbation we use WKB. I think maybe for all of you guys, first time heard WKB is in the quantum mechanics, right? So it's the same thing, similar thing. But here we can apply this method to do the black hole perturbation. And okay, so in black hole perturbation theory, the linear sphere equation can often separate into the couple differential equation. Sometimes it's one radial equation, but sometimes it's radial and the axial equations and angular equation for curl-like, something like that. So, but all of them are ODE, linear ODE. So it's a perfect target to use WKB approximation to study some fundamental phenomena. Yes. Okay. And for linear perturbation, black hole perturbation theory actually is quite hot topic now. I think many people working in it, and so basically they can provide some famous physical phenomena. Is something like quasi-normals. It already observed from the gravitational wave, of course, but the details still not yet very clear about how to analyze it. But this is other topic, so we will not talking about it today. And quasi-bound state is something like a complex bound state also. And super radiance, I think I know some of you guys working in super radiance, and gravity factor also we working in gravity factor. And gravitational wave emission is something like what I say, further analysis to quasi-normal and analysis the ring down wave and latent tail and others. For example, more is the stability of the black hole. If the complex part of the solution diverge or converge is another question. And so many of the physical phenomena can.
What is the quasi-bound state?
It's a barrier. It's a barrier, but sometimes they have the deep. And if there are local minimum, and you can impose some boundary condition, it's something like no ingoing and no outgoing. Then there are some bound state, but the bound state, as I know, is still the complex. Yeah. Okay. And but basically in this talk we talk about WKB. So the most sufficient for WKB approximation is study the cosine normal and gray body factor. And others, you can also use WKB, but you need to apply some more thing. Yeah, but that is beyond the scope of today's presentation. Okay, so this is some, as I say, I focus in cosine normal and gray body factor. So the cosine normal is here. Oh, the light is here. Yeah, the cosine normal dominate the ring down behavior. So this is this is the it's a model, and this is the real observation for the very first gravitational wave. So far now we already confirmed this is the cosine normal damping, but we don't know what is the linear combination. It's not yet, the signal noise ratio not yet big enough to talk about it. And this is some picture I took from asking AI and asking to give me some picture about the gray body factor. Actually, it's something like related to the Hawking radiation. And the idea for the Hawking radiation is a pair production around the black hole horizon. It's something like a quantum fluctuation and the pair production there. And the antiparticle fall in the black hole, and the particle going out from the black hole. And the black hole spacetime will have something called the effective potential, like this is what we're going to show today, is basically a barrier. And then the black hole perturbation can tell us the transmission probability, or we call it gray body factor for the Hawking radiation, how much probability they can transmit to the place that we can observe. But so far now, we not yet observe Hawking radiation. So we still cannot confirm it's a real physical thing or just a mathematical toy for us. But as I know, I heard some talk maybe early this year is talking about the Hawking radiation, observe the Hawking radiation from the gravitational wave for the and the signal is from the primordial black hole in the early universe. And this will making some gap between the early universe and current universe. But you can search primordial black hole Hawking radiation, and they will have some paper talking about this, but and it's possible to observe, but so far no, the gravitational wave experience is not yet go to that level, but it's possible in the future. Okay. So this is the important reference today. And the first one is I think it's the Bible, or something like the highest Buddhism book, something like that. If we believe this, and everyone will read this, is Iron Will is in 1987, and the WKB approximation for the black hole, and the second, they work in the third order approximation, and Konopia he do the sixth order approximation in 2003, and Opla and I cannot pronounce his name correctly. They do the 12th order and improve the semi-analytical approach because WKB, if we go to higher order, you will have some diverge problems. So they use another resummation method, it's called that Padel approximation, to constrain the divergence. And then it's this paper, 2017 and 2018 Konopia also use this. But the key improvement for this, the 2018 paper, is he provide the program. So from the complicated programming, everyone need to do and do it again and use a lot of time. But in this paper, he provide the program and everyone can use. You just need to put in your model and you can start it. And the blue mark here, I mean, the small number of blue number is, as I checked, until yesterday, there's citation. Yeah, so it's quite huge citation for this kind of main articles. And so that's why I think if you want to work in black hole perturbation, then you can, if you have time, you need to read it. Okay, so this part is introduction and summary, right? So I just give you the result first, the result. Okay, so usually from the black hole perturbation, we will go to a single radial equation like this. Okay, so this is basically for spherical symmetry, but for Kerr, you know, there is a axial equation and angular equation, and you need to define the angular equation first, and by the end, you also back to the radial. Okay, then is a second order differential equation in the Schrödinger-like form. And also you maybe you know or you don't know that all the differential equation, second order differential equation, no matter it has first order derivative part or not, you can simplify it into the Schrödinger-like form with some transformation. So actually the Schrödinger-like form like this is quite well used. I mean, can suitable to use for in many cases. Okay, but okay, so in black hole perturbation, usually if the simple case is something that we can rewrite the Q, we can find is omega squared minus V effective potential. And the effective potential is something like here. We say usually it's a barrier, but not all. Okay. Okay, and then you can define some expansion around the peak of the potential, then define this kind of variable. Then I directly give you the formula, like you can derive the gray body factor like this, and using the above coefficients, above parameters, which means if you have a space-time and you do some perturbation and no one do it, then you derive, you follow a long process, then derive the separate radial equation, then you put in here, and you got the result, approximation result from WKB for the gray body factor. Okay, and the same for cosine normal is like this. Okay, so for cosine normal, you need to solve this, and this V0 is the same as previous page. You expand around the peak, and then derive put okay, you got the value of maximum, then you put in is V0, and the V perpendicular is your derivative for 2 times, then put maximum in, and you put all these things in. Then you can solve cosine normal. Okay, so it's quite convenient that in some sense. So basically, wherever you obtain a new second order ordinary differential equation, that sometimes it's mainly no people work on it or no people obtain it before, then you want to submit your, you want to do something, can publish, then you put your case into this formula, then you got the physical quantities, then you write down, then you can submit. So if you can handle this kind of method, then congratulations, you maybe is going to graduate, or you can see your next publication in the short time. Okay, so sorry. So it's a summary. So thank you for your attention. Okay, so I put this slide here is just want to gain some how to say this, I don't know. Okay, so basically, however, however, we have total 8 page, so this is a nice page. So it's normal, right? So however, let us start again and take a closer look at the whole procedure following the third order WKB approximation from this paper, Iron Will 1987. Okay. Okay. So this is the real outline. So previously we just give the introduction and summary, right? So to know how to use this approximation to study cosine normal or gray body factor, you just need to use the formula I showed before. Then you can, for most of the case, you can do it, and some of the case you need to do some more complicated expansion, or maybe you need to set some parameter, but you can still use. But to know how to get this WKB approximation, actually the procedure is quite complicated. So in this case, in later, it's a review, right? So we follow the Iron Will third order. So all this is third order result, and there will be we will starting with general solution, then interior solution. So also we need to talk about why we need interior solution, and exterior solution, why we need exterior solution, then matching and why we need to matching. And lastly is a remark, because I gave summary already, so last is a remark. Okay, so the general solution is WKB approximation, as I say, is the exponentially expansion. You assume the wave function solution is an exponential expansion, right? So as a serious solution, we usually put exon to checking the order, and exon here is no physical meaning, it's just for checking the order. Then later you can compare different order, and you can solve it order by order. And I don't write summation here, but you know it's a sum because it's contraction. So it's something like you need to sum over all the wave function. Okay, so if you write down it explicitly, then put in the radial equation. The general form is like this. Then exon is here, right? And also here. So when you put in, you can collect the exon order. And the whole equation equals to 0. So you can solve it equals to 0. Order by order. So the leading order is only this. Oh, I lost a square here. Sorry. There is a square. And plus QS equals to 0. So S0 can be solved as this integration. And the exon order is this one. This one, okay. So you solve it, then you can get the natural log QX. Okay. Okay. And the third order, second order is on second order. The recurrence relation is like this. Then you solve it. So S2 will be an integration of this thing. And also exon 3 order. You can solve like this. It's also integration, but it can simplify to something like non-integration. But as I know, mathematicians don't like this. This kind of simplify, but for us, we can do it. Okay, so total is coordinate, or x. Here is x. I don't want to say total is coordinate now, because different space-time, different perturbation, they need to define different total is coordinate, right? So here we just keep it in general. It is x, yeah, x coordinate.
But the horizon is that
For structure is, yeah, but horizon. I think most of the case spherical symmetry is right. Just the spatial infinity projection will be different, but anyway, it still can use this because now X is in general we don't give it any constraint like what is X. Okay, so if you follow that the iron wheel paper, I think the first thing you will, the first struggle point is how they define the ingoing and outgoing wave. So for S0 is the leading order in previous page, right? And when X go to infinity or go to, okay, we keep it as infinity. And S0 is approximate to plus minus this. So the plus is right moving, so let's call it outgoing. And the minus is ingoing or left moving. And also the X go to minus infinity usually is in the place of horizon. And K here is in some sense you can treat it as a constant, but basically it's for spherical symmetry and the rotational black hole is a little bit different, but you can treat it as a constant. Now, and the S0 for plus minus sign is it is like okay. It's go to plus minus ikx, and remember now x is minus, so the plus sign represent the outgoing way to the horizon. They call it outgoing in this paper, but sometimes later we call it ingoing to the horizon. But now they call it outgoing, so their out is outgoing to the horizon, ingoing is ingoing to the barrier. So this is the how they choose the ingoing and outgoing condition for this kind of solution. And then this is a general solution already. So which means you have a Q, you have an effective potential. And if it is analytic anywhere, then you put in, and this is the solution. Okay, so this is what I mean. The WKB solution is there everywhere except near the classical turning point. What is classical? You can treat the this line is omega square, and this is the effective potential, and the whole diagram is the Q. So omega is something we want to solve, but we don't know what's the value of omega. So it's possible they have some turning point. Maybe 2 turning point, 1 turning point, or no turning point. So if we want to study it in general, we need to treat it as a turning point problem. Which means in this turning point, Q is vanished, right? Then the solution, you cannot put Q vanish in this kind of turning point. So this kind of thing diverge. Then the solution diverge. Okay, so for the turning point or the turning point region, we need to do some more thing. Okay, so basically this plot is from the paper directly, and they separate to region 1, 2, 3. Okay. Okay, so this is so far the general.
But sometimes it be effective. Depends on omega too.
Yes. So omega is something we need to solve. Yeah. So we don't know. And here is they keep it in general. So it's possible to have 2 turning point, 1 turning point, or 0 turning point. Or even 3 if there is a dip and the omega is larger than asymptotic behavior and there is a dip, maybe 2 or 3, right? Yeah, so but here we just focus in the barriers, and identically we can treat it minimally, maximally is 2 turning point problem. So basically they work in the 2 turning point case. Okay, so therefore, we can say the general solution is okay here and okay here. But in the middle is more complicated because omega is something you need to solve. So you don't know what exactly region 2 is. And inside region 2, there are some places the general solution is not okay. So that's why they need to do the interior solution. So you okay, you can see the turning point is here, and the maximum is here. So basically, we can do the expansion around the maximum, and we know that the turning point will be supposed to be close to the maximum. So firstly, to do the interior solution for the middle part, region 2, we do the expansion for Q. Q is omega squared minus V effective, right? So it's supposed to be total is coordinate dependence or radial dependence. And here we do something like transformation, like Z is defined as X plus minus X0, and X0 is the position of the maximum peak. Then you do the tidal expansion to the whole Q, then you can write down this. And you define this is something like BCD is the coefficient, like what we need to use to solve gray body factor or cosine normal in the very beginning. But the coefficient is from here, is defined as this. And because we do the third order, and so we do until Z6. And then this is the new differential equation in the region 2. And people find it, if we define the new parameter again from B, C, D, F to B bar, C bar, D bar, F bar, then the leading order here, is parabolic cylinder function. So that's why we need to redefine the bar as this. Okay. Then the whole differential equation transform to the something like depends on T and B bar, C bar, D bar, F bar, something like this. So this is our new differential equation need to solve. And the most convenient way, because we say is the leading order is exactly parabolic cylinder function. So we set phi is something like a function of T and the parabolic cylinder function. But parabolic cylinder function inside is another GT, another function. Then you put this setting inside this differential equation, and you will get this. I forgot the stage. It's new plus 1 here. So the leading order is parabolic cylinder function, and this vanish because this is just the ODE for parabolic cylinder function. And the first order derivative coefficient, you can solve it as a V when F equals to G dot minus 1/2, then this term also vanishes. So by the end, you put this back. What you need to do is a new differential equation related to G. You only need to solve this. So solve this, we use another series. Where we set G is something like this, and A is a series of T. And here in the paper they don't put a bracket, but here I think it's better to put bracket because this is not square or cube, it's just a notation. So I put a small bracket here and put everything, this kind of thing in this differential equation and solve seriously. I mean, solve serial and order by order. And then you can get the result of A. Okay, but in some sense, okay, so this is something like you go in and you know, and okay, by the beginning, if you read the paper, for the mu plus 1/2, this definition they plus something, but actually at the beginning you don't have. But you will find. Firstly is A2. A2 don't have constant term because you can say A2 is T proportional to 1 and T proportional to 3. And the whole radial equation, if you put in, they don't have constant T order. But there are something left in the constant T order. So that's why you need to put in by hand with an unsolved thing, like put in here, put in mu plus 1/2 is okay. I write it later. You need to put in I mean the big lambda in the last second line. So this is from solving A2. If you don't have this term, the constant order of T will not vanish. So you need to put here. And then for solving A4, the same. The constant order of T cannot vanish. So you need to put the Eson square big omega. Okay, so that's why the final expression including these two terms. And because we know the result already, these two terms are quite important for the study of cosine normal because they just give you the solution through this formula. But anyway, these two terms is put in by hand and solve to vanish the constant order of A2 and A4. So this is for third order. So for higher order, so maybe A6 or A8, then okay. So you will have more constant like this. Okay. Then the solution. So even this is put in by hand, but this is the solving the vanishing of the constant order. So it's in some sense you're solving it order by order. You will solve this coefficient first, then solve this, then solve lambda, and for higher order also. So it's something solving order by order, and this thing will relate it to the bar parameters that we showed before. And you can transform the bar parameters to the non-bar and transform from the t coordinate to the z coordinate and transform back to the tortoise or x coordinate, right? So the whole thing is linked together, but the interior solution is something like this. And the general form for the interior solution is given by this. And I don't show the detail of how to write down this parabolic cylinder function in higher order, but you can go to the paper and they show whole expression. But as I checked, one of the expression is until second order only. So if you want to reproduce all the result, you need to put in one more higher order of this parabolic cylinder equation. Parabolic cylinder function, yes. Okay, so basically this is an interior solution. Okay, so we talk about general, we talk about interior. Then another thing is, okay, I need to back to the picture. Around here, when they close to the turning point, the WKB is starting to getting not so good. So you also need to do something like exterior solution around the turning point in the region 1 and region 3. Okay. So exterior here means the overlap region with region 2 in the region 1 and region 3. So that's why it's exterior outside the turning point. Okay, but it's even it's outside, it's overlap region with overlap region with region 2, right? So you can still use the peak expansion Q. But it's not exactly a peak. It has some Z bar different. Then you can define the Z bar like this. And if you check, you put Z bar in the above equation, then it back to the tidal series of Q around the peak. Okay. So this is the new Q for the exterior solution. Then, because this is region 1 and 3, the WKB is still possible to work. Then you can put this Q into the general solution, S1, S2, S3, S4. And doing the integration, then you can get this result. And I think the iron wheel paper is reliable. Is all these kind of coefficient you can check, and exactly the same. I check, so you can check also. Yeah, it's just putting this Q inside the general solution, then you can solve it order by order like this. Not order by, just mathematical solving and integration and collects the term you want. Of course, they will have many higher order term, maybe the 10, the 20, something like that, but you collect the order you need, and it's like this. And the efficient order also a problem, but so far here is reliable. And okay, I just say this is not. Then if you have S1, S2, the exterior solution is like this. And one trick is when you're doing X2, actually the integration diverge here. So you need to do 2 times the integration by part and do the integral for this. Then it's okay to do. I think there is another famous book, is Bimmer talking about WKB. They do this is doing 1 times integration by part, but the lower limit you still need to use Z plus mu, an unknown parameter, and this parameter assuming vanish for the proportional terms. Then actually the result is the same. You can do 2 times integration by part and do the integration here. As I check, is exactly the same as what in the book talk. So the trick is here. And the coefficient before this need to exactly converge to mu plus 1/2. This is also another trick like you need to check when you're doing the, which means this thing and this. So far, only S0 and S2 has natural log term. And put in the phi. And this term will, because it's exponential natural log, so it will go up to the order, right? Then you need to exactly converge to mu plus 1/2. Then this is something like you need to check in process, like check you do it correctly or not. Okay. So this is the exterior solution and matching. So once you got the interior solution and you got the exterior solution, exterior is from WKB and interior is from parabolic cylinder function. So actually it's 2 different things. But in some sense, if it is a full picture, then you need to do the matching. So the exterior for region 1 is this, the first equation, and for region 3 is this. And the interior is this. And here, so far, I copied from the paper. This is just the leading order. But it's not the leading order. It's the third order WKB contribute to the leading order. Okay, so this is something like even is leading order, but it's still different from other leading order. It's something like third order WKB contribute to the leading order. So after matching, you mention Z1, Z in 1 with B, and Z out 1 with A. This is one side, and you got A as a coefficient, A and B related to Z in. And you put in A and B related to Z in here, and you matching another side. Then this is the whole picture for matching. So after matching, it looks ugly. It looks super ugly, and what you do is also very super ugly. But the result is clean. And this is, they call it leading order result, but at least this term contribute for the second order. This term contribute from the second order. And then we have the general solution for WKB approximation in black hole perturbation. Okay. Okay, so lastly is a remark. Okay, so if you remember at the beginning, I showed you the general formula of cosine normal. And if some of you working in cosine normal, you know the boundary condition is, if I follow the language of this paper, is purely outgoing wave to the event horizon and purely outgoing wave to the spatial infinity. But sometimes we say purely, if we define the left moving is ingoing, it's something like ingoing wave to the event horizon and outgoing wave to the spatial infinity. But here we follow the notation. So it's purely outgoing wave to the event horizon and outgoing wave to the infinity and ingoing wave to the barrier. Okay? So for cosine normal, firstly, we choose one parameter is 0 for the boundary condition. Then we got Z out 0 and this kind of thing. And this is gamma function. And gamma minus integer is diverge. Okay? So in this case, we know if mu is integer, then Z1 need to be 0. Then Z in 3 and Z in 1 be 0 is the boundary condition for cosine normal. Then it's automatically satisfied the boundary condition for cosine normal already. So we know for cosine normal, mu is integer. Then we put Z0 square as this, put in here. And as you remember, this is the equation we solving for solving interior. So we have big lambda and big omega, and maybe higher order there are something more. We put this in, and solving omega, then it becomes the complex frequency as cosine normal. So that's why this if we got the general solution like this, and it's quite straightforward to solving the cosine normal, and all the barrier potential can go to this general solution. So that's why WKB, that's why they have a lot of citation. Okay, so this is for cosine normal. And for gray body factor, also from previous matrix, and we also take Z in this direction is vanish. So now we have Z out 3 and Z in 1 and Z out 1. Okay, so it's the spectrum for the, if you have a wave coming from infinity and here, and it reflect and transmit. It's the same as if you take Z1 in vanish and keep others free. Then two expression is equivalent, you can check by yourself. But here I just choose one to show. Then you have this kind of relation. And previously, we know Z1 in vanish is because this integer, but for the gray body factor, mu plus 1/2 actually is pure imagine. Because I just show very quick about lambda and omega. So if I tell you, I can tell you lambda is imagine and omega's related to mu plus 1 first order and third order, so it's still imaginary. So the whole thing mu plus 1 half imaginary. So this is not necessary to be infinity. Then the second equation gives us this. Then we put z out in the first equation, we got the coefficient like this. And as we know, transmission probability is defined as this absolute value square. And in this process, we simplify the equation here with the relation of gamma function. And mu is pure imaginary. So that's why they have this relation. And t is something like this square. And another thing is, if this is pure imagine, you can check R star is equals to this 1 minus 1. R star is this. And this is pure imagine, so you can minus. And minus 1 will give you exponential minus 1. I pi, right? And I pi multiply mu plus 1 half divided by 2. So you got I pi mu divided by 2 and others. And this also complex. So in the complex conjugate, you need to give a minus and minus and minus. Then you will find a relation like here. So the absolute value square is R star multiply R. Here R star minus 2 multiply R minus 2. Then R cancel out. So actually R did not contribute to the gray body factor in general. But this R is from the matching procedure, but it did not contribute to the gray body factor if they satisfy this relation. So by the end, the transmission probability, this absolute value square, can be simplified as this. Then we define SW is I pi mu plus 1 half, and mu plus 1 half is this kind of thing. And because it related to mu plus 1 half also, so you need to solve it iterationally, and you can write down the approximate formula of S omega. Then you put everything in, then you got the gray body factor. So this is the review for the beginning pages is this and this. Why through this method we can write down this kind of general formula quite quick, and it seems like suitable for all kind of case. Most of the case is because actually they solve it in general. So for any case, and you just put in and you can get the result. Okay, so remark. So thank you again. Okay, so any questions?
So thank you so much for a nice talk. Are there any questions from the audience? Please
Yes.
feel free to ask. Yeah.
Yes, I have. Basic. When you write the Schrodinger, what's the physical meaning for psi function in the context of black hole perturbation? And the other question is about watching normal modes. Do we need to know the gray body factor in advance, or we can treat them independently?
Oh,
Thank you.
firstly, gray body factor and cosine normal are two different things. Cosine normal describe the ring down of classical wave, and gray body factor more like quantum tunneling. So it's different thing. Yeah, and the physical explain, actually you can treat it as an ODE only. But if you consider some field and in some space-time, then this become meaningful. It become the wave function for the field in such space-time. Yeah. So, but this one is in general. So we want to address this in any space-time or any kinds of field at the beginning. We just treat it as a general Schrödinger like ODE.
Can we get the probability to get something from this context, or
Yeah. We don't have exact number because now we don't know what is we don't know what is V. This depends on field and the space-time. Sometimes V also depends on omega, and sometimes it including complex, many kinds of case. But at least we need to know what is V. And usually this is the most difficult part when you study the perturbation. You need to find some way to separation and finally write down what is the effective potential. And unless you got V, then you can try this method to get the solution.
Thank you.
Because we are running out of time, so maybe there's one more question. Are there any questions from the audience? Okay, otherwise, I got a question, one last question for you. So basically, would you mind to explain in more detail what are the limitations of the WKB approximation in black holes perturbation theory? The limitation.
Limitation is, okay, so firstly, the effective potential, at least then it has a explicitly barrier. And the maximum is solvable. Or you can use some approximation to solve the maximum, also okay, but the whole spectrum will be changed. And this, the maximum is solvable, then you can use. Yeah. Yeah.
And what if the effective potential goes to infinity as R goes to infinity?
Oh, it's different cases.
Like for ADS.
Yeah, it's always Houdini because the boundary condition be different. Yeah.
So for the ADS, there's some solution.
There are some solution, but it's no physical meaning. And I write it reject by all the paper, all the journal, famous journal all reject because they say this is non-physical, meaningless. Yeah.
So people usually go with
Yeah, or continuous fraction maybe can also do the ADS case. Okay. So thank you for your attention again.
Thank you, everyone. Thank you
However,
for the speaker, please. So it's time for the break.
so I changed the page like.
Oh, actually, you got 48 pages, or we still have 2 or 3 minutes if you want to continue with
this
your.
is the last page.
Okay, that's a large page. Okay.
Yeah, but you can remember 48. Yeah, because I'm going to have some related publications soon, and 48 is key value in that thing. We don't know why, just like the 48 here, and it appear everywhere. Yeah, that's why I put the last page as 48 and 28, and maybe you can buy the lottery. I tried for 2 or 3 times, but it failed. Yeah. Okay. Thank you.
Thank you, everyone.